Morning, everybody. How's everybody doing? Pass out some cards here. While I'm doing that, what did y'all learn last week from our two visitors?
Research.
Pardon?
Research.
Research? Okay. What about the research? Anything catch your eye? What kind of research do they do?
Who they tried? Wasn't it? Or they tried something?
They are involved in some HIV research, that's
Yeah.
true. What about it?
Isn't it a drug for instance?
Yeah, so they're making potential inhibitors for testing against a particular enzyme. I forget the name of the enzyme in HIV. Yeah. What else did you learn? Do they work with undergraduates? Yeah.
Undergrad.
They do. They do research in general, what you would call organic chemistry. So, studying the use of carbon and other atoms to make molecules that might have medicinal value as for anti-HIV purposes. Anything else? Does the research maybe something you might want to do when you think about your capstone? Anybody? Yeah? Anybody think about making an appointment with them and talking to them? Yeah. Be good. Go ahead and make an appointment, talk with them, get involved. Would be a good idea at this point. So, this week I gave you a couple of things to read and watch. The first one was this article out of CNE News called Designed to Disintegrate. Degradable electronics. What did you take from this particular article? Why is this area important?
Because it gives us a less invasive way of monitoring people's illnesses.
Okay. Why is it important that these things degrade? How does it promote less invasive?
So you don't have to perform surgery to remove.
Okay. Yeah, so imagine being able to implant a device that monitors your heart rate, provides electrodes to stimulate your heart, helps control the release of insulin, whatever the case may be. And that over time, that particular device just disintegrates and degrades into things that are essentially harmless. Right? Where else might this type of technology be important? Is this normally how we think of making things? Do we normally want to design things to die and disintegrate at a particular point, or do we try to design things that have longevity? Usually we think about longevity. How can I make a durable plastic? How can I make something that lasts 50 years? How can I make a car that runs more miles, right? That's how we typically think about things. But in this case, we're talking about how do we take things that typically last a long time and make them degrade over time, okay? And at least with a particular amount of time. So that's pretty interesting. What does chemistry have to do with this?
The breakdown of the building blocks of the device.
Yeah. So when we think about the material, we have to think about not only can we make a material that is robust and does what it needs to do, but how can it break down over time, right? How might some of these types of materials break down? Is it time? Does time make it break down? What makes something break down and disintegrate? What makes something biodegradable? Let's think a little more general.
usually it has to do with, I can't remember what it is. There's something that, well, I know like in nature, you'll have things like bugs
Uh-huh.
and stuff like that eat through decaying wood. things
Yeah,
like that.
yeah. So, I mean, if we think back to nature, wood is a pretty robust material, really, except it can degrade under certain conditions, right? What kind of conditions are those? You said bugs, so let's,
Right.
hopefully we don't have bugs living in us, so let's not think about that. That's kind of a disturbing thought.
Usually warm environments, they waste biodegrade.
Warm moisture,
Warm moisture,
right?
yes.
All right. What about the human body? What do we have a lot of?
So like enzymes and stuff.
We have a lot of moisture. We got a lot of water, right? And we got a lot of
Enzymes.
enzymes. We have things that are machinery that's actually built to degrade things as well, right? But we're mostly, if you've ever watched Star Trek, there's this one episode where this alien life form calls humans dirty bags of water, right? And that's really what we are, right? We're mostly water. And so we got a lot of water. So maybe we can make a material that slowly degrades in the presence of water, right? That's kind of cool, right? So we could do that. What else might contribute to the degradation of something?
Antibiotics.
Antibodies could, yeah. I'm trying to think simpler than that, though. What else do we have? We got water. Talked about enzymes. Talked about antibodies. Right. Oxygen. Right. Oxygen oxidizes things and makes things degrade. Right. That's how we burn things. You can think of things slowly burning. In fact, when we're inhaling oxygen, our body is slowly burning. When we say burning calories, right, that's not figurative. It's just not a huge flame, right, that's engulfing. But oxidation is the process, right, of burning things. So you can think about that as a possibility. Anything else that you can think of? Acids, right, so pH. Right, is our pH of our entire, do we have a constant pH in our body? No, we have different pHs in different locations. Medicinal chemists use this all the time, not for this purpose, but just like Andrew said, we've got stomach acid, so the pH would be high or low?
It'd be
Low, right, so low numbers are high pH, right? What about when it goes from the stomach into the colon? What starts to happen? Or the intestines and the colon? The pH starts to go up, right? It becomes less acidic, right? What about the blood? It's around, it's a little on the basic side. It's about 7.3, 7.4 if I remember right? And so medicinal chemists will actually use the different pHs of different compartments in our body, if you will, to trigger medicines. In fact, there are areas where, or some of the medicines that you take are actually not the active form of the medicine that really your body needs when you take it. It'll get into an acidic area or a basic area and it will change. It'll undergo a reaction that allows it to transform into the medicine. And so you'll learn about that kind of stuff if you ever take medicinal chemistry. But you could imagine, right, making a material where, if you swallowed the pill that's got the electronic device in it, maybe it's active at high pH, or low pH, but when it gets into the intestine, where the pH is higher, it starts to degrade. So you could imagine using those types of things to influence the degradation of these types of materials. And so we have a whole school across the road here called the School of Polymers, right? And polymer engineering. And some of those folks over there think about these types of things. How can we make a material that does what it needs to do, but then degrades over time, right? And many of you have probably, not so much with medical devices, but probably have come into contact with that type of stuff when you go buy products and it says this is biodegradable, right? It is a process by which we can control the decay of this. And so this is an important area of being able to make these small devices. Things have come a long way. in many years in the medical field. They actually now have, doesn't talk about it here, but they actually have a little capsule now. It can't be much bigger than that you can swallow. It has an entire camera in it, and the doctor can watch it go down and see what's going on in your esophagus or in your stomach or wherever it is. And so used to they had to stick a big old scope down, right? We can now just swallow a little pill and see this kind of stuff. But it'd be kind of nice if that could just kind of degrade, and come out a lot easier than it probably does now, so to
I wonder
speak.
if they can make ones that are degradable but also healthy for your body still. Because I'm thinking of the after effects of
Yeah.
those cells.
Yeah, so just because something's degradable doesn't mean that what it degrades into is safe, right? So yeah, that would definitely be something that they'd have to think of. In other words, you wouldn't want a material that contains a lot of cyanides. You'll learn about those when you get into organic chemistry. Those are called nitriles. Y'all ever wore nitrile gloves? Yeah? Well, it's got a lot of cyanide in it. Not toxic cyanide, it's organocyanides. But if that degraded into real cyanide, probably wouldn't be very healthy for us, right? I mean, cyanide can kill us pretty quickly. So, yeah, when they're thinking about this, you got to think about what it degrades into as well, for sure. I also wanted you to read this cool coatings cover story. Why did I want you to read this? Okay, that's true. What else? What's one of the biggest threats to humanity right now? Climate change. Yeah, you can call it global warming, you can call it climate change, you can call it whatever you want. It feels cold outside, so people are going, where's the global warming? Well, this is local weather. Global warming is what happens on a global scale, and we do know that the temperatures are rising. Debates certainly rage about what is causing that, but I think the consensus is getting closer and closer to it being humankind activity impacted, right? So, why would it be important to be concerned about coatings on buildings? How can that fight climate change?
Good insulation and conserves energy.
Yeah, right? So, I'll give you a little bit of a history lesson. If you went and saw my grandparents' house, it was built in the 1950s, so getting pretty old now. When they built houses where I grew up in Oklahoma, they did not put insulation in houses. There was no insulation in my grandmother's house. Why do you suppose that is? Huh?
I mean, it wasn't a thing yet.
Wasn't a thing yet. Why might it not have been a thing yet?
Too long ago?
Huh?
It was too long ago.
Too long ago? Well, it was a while ago, I'll give you that. But why did people think that just building 4 walls, having an outer thing and an inner sheetrock and nothing in between, why didn't they care about putting something in between? Turns out natural gas was dirt cheap back then, and well, heck, we can heat and cool our house cheaper than we can insulate it. So it was an economic thing. They just didn't do it, right? And so as you can imagine, my grandparents' house used a lot of natural gas, contributed a lot of CO2 emissions, and partially responsible for where we are today, right? So now we put insulation in houses. But now we're talking about how we paint a roof or how we paint a building. How might that impact climate change? What did they talk about here? How can paints help us out?
Because the less energy that we're using, the less natural gas is being burnt at the energy plants.
That's true. That's true. But how does the paint help us? How does it get us to the less part? In the summer, do I want heat coming into my house?
No.
No, I want heat not to come into my house. But what about in the winter?
You want it to rotate
You want it to
the heat that's
I want it to
outside.
You want it to what?
I want it to burn.
don't like the cold.
You don't like the cold? I don't blame you.
Be very glad in the class.
It's not that cold.
Tears in my eyes.
So in the summer, what kind of a coating am I going to want? One that reflects heat or light or UV, or not UV, but infrared, right? Heat. What reflects things? Metals will reflect things. What else? White, light colors, right? So in the summertime, I go out and I paint my house white. So it reflects the sun and it helps keep my house cool just by that simple act of reflection. Right? Now, what do I want to happen in the winter?
Black.
I want it to be opposite. I want it to be a dark color, black, right? I want it to attract, to hold as much of that in. So, around March, I go out and I paint my house white. Around November, I go out and I paint my house black. What's the problem?
There's a lot of rain.
I paint my house twice a year, right? I'm going through a lot of stuff. So what do I need?
Something that adapts.
I need something that can respond to the changes in temperature, right? That's what they're really talking about. How can I make a coating that when it's hot outside, it's lighter and it reflects more sun or heat away, and in the winter it becomes darker and absorbs more,
A mood ring.
right? Pardon?
I was thinking of a mood ring.
A mood ring? No, that's exactly right. Yeah.
Those mood paints that like when
Yes.
you touch it
Changes with the temperature.
Yeah. And what about my glasses? If you've ever seen me walk outside, when I walk outside, my glasses get dark. And when it's cold outside, I'll walk in and my glasses will stay dark for a while because it's cold. So there's temperature plays a role too, right? So if I can make something, if I can make a coating, then when it's hot outside, it's light, it will reflect the light. That'll help keep my house cool, right? And in the winter, when it's cold outside, the coating becomes darker. It helps absorb the heat from the sun and keeps my house warmer, simply by applying a layer of paint. That's pretty cool. That means that I don't have to have as much of my air conditioner running or my heater running at the various times of the year because I can use the natural heat from the environment to my advantage. And so there was a lot of reading in here about energy hogs, right? Running an air conditioner takes a lot of energy. Running a heater takes a lot of energy, even when you figure all of the energy efficient appliances that we have, okay? So it's your biggest consumption of energy. That and heating your water are the biggest energy consumption things that you have in your house these days, okay? And so cooking food's no longer at the top of that list, no longer is it the television. When I was a kid, the television put off so much heat when we had it by a window, and in the winter when it would frost over, it would actually melt the TVs. Don't do that anymore. They don't put off any heat with the LEDs, right? So you don't really have all that going on anymore. But here's an example of a dye that can change colors based on heat, right? So if you take this and you put it in heat, it looks like this and it's white, right? And then as it gets cold, it actually changes its structure and it becomes darker. So all I've got to do is put that in a coating, right? Use that then, and then in the summer it's white, and then the winter it's darker. I don't know exactly what color it is. And so you can use this type of technology. What are some problems with this, you might think?
Don't go with the house decor.
Huh?
Don't go with the house.
Don't go with the house decor, okay, maybe.
Homeowners Association.
Actually, personal preference things are important, right? We would want to have at least some choice of lighter colors, and we'd want to have some choice of darker colors. Not everybody wants a black or a white house.
Because what if it's pink?
What if it's pink?
Right.
I wouldn't like that.
You wouldn't like that? Yeah. But as consumers, we want choice, right? We do want some choice, right? So they have to be thinking about this, and I'm sure that they are. What else might be a challenge for us? Cost. That's exactly right. I mean, if it's gonna cost me $25,000 to paint my house, just for the materials, you know, you're probably not gonna do it, right? Okay? Or if it takes some type of special trained person to come in and paint it, you know, probably not gonna do it either, right?
Actually, I'll be that person because that sounds cool.
What else?
Will it go back to like, cause
Yeah, so this has to be completely reversible, right? It has to be able to go from light to dark and then from dark to light. And it has to be able to do that at least twice a year, right? And how long do you want your house to be, a paint job to last? Probably at least 10 years or more, right?
And I feel like it would get muddy, like in those in-between temperatures. I'm sure, like, not everything is going to change all at once. So, like,
Yeah,
or
like
say
weather.
the sun is shining on your house. Are you just gonna have one spot that's white and the rest of it's like gray?
Maybe.
Is
That might be interesting.
That's kind of cool.
The north side of your
Right.
house might be one thing. And so what you're talking about would depend on light. But if we just did the temperature, right, usually the front of your house and the back of your house may not differ
Too much.
too much.
But
And
that's
I mean, it
still gonna
can.
be some spots.
But I mean, you know,
Yeah,
in Hattiesburg,
right.
Mississippi, when it's 95 degrees outside, it's 95 on the north side. The air temperature is 95. Now, the walls may be hotter, but it's going to be hot, right? If you're in Antarctica, it's going to be cold all the way around your house, whether it's facing north or south, right?
But if they tried to build this in Mississippi, I kind of feel like the technology would just die from exhaustion.
From
We're trying to go from, oh, it's 41 degrees out. Oh wait, no, it's 90.
In Mississippi.
Okay.
Yeah.
So yeah, we could have fast swings, right? What else?
Use that temperature, just change it.
Uh-huh. What else? I mean, these things have to be able to last, right? They have to be able to stay in a coating. They can't you don't want it to be able to wash out. I mean, obviously there's a lot of rain. How durable is it gonna be? Are those dyes gonna be something that, you know, in the presence of air, are they gonna oxidize and slowly degrade over time? You know, so this is a case where we wanna build something that's robust and less degradable, right? So you kind
But we
of.
also gotta make sure we have enough materials for it.
Yes, there's always that question. Do we have enough materials to available? And in this case, since it's organic, I would say we probably do. Okay. So imagine being able to put a coating on your roof that is able to reflect light and collect light, right, at different times to do what we need to do to help us cut down on our energy use. So I think that's pretty cool, being able to do a lot of this kind of stuff. The quote here was, "I want my bills to be lower and I want to have higher comfort, but it's a fairly complicated system," right? So right now, we're just not there, but I think this is probably maybe 10 years out where you might see new houses being built where in the summer you will go by and you'll say, that's a little different shade than I remember it being last winter, where these things can adapt and change.
Wouldn't that change marketing?
Huh?
Wouldn't that change marketing?
Marketing? I don't know.
or it make the houses more expensive because of the paint.
Could very well.
Yeah, but also, if you're thinking you're buying a black little rooftop house in the winter, and then in the summer you're like, oh.
Yeah.
They'd have
That's true.
to tell you that the paint is on there. I mean, I doubt you would buy a house and then you walk outside and your roof is white and you're like, what just
They don't tell us about our roofs now. Not really. Like, hey, your roof is painted with blah, blah. And you're an eco-friendly person. You're like, that's not safe.
Well, you know, there may be challenges with this. I mean, you're pointing out some valid things that might come about from this. All right. All right, the last thing that I wanted you to do today was view the conversation. Oh, that's a terrible picture. The view of conversation with Madison Hanson. Why did I want you to watch this video? What's so special about Madison?
She took a less traditional route and still succeeded.
Yeah. So what was her a little less traditional route?
She was a double major in music and biochem and didn't add the biochem major until like her sophomore year, I think is what she said.
That's about right, yeah. That's about right. So why did she add it? Why did she add the biochem?
Like it was really close to pre-med. She said she only needed to take a couple extra
And she didn't
classes.
like biomedical sciences.
Yeah, she started off being biomed, right? And decided that she didn't like biology as much. Now, this isn't a talk against biology. I have nothing against my biological colleagues. But it's not for everybody, right? And you don't have to be a biology major to go to med school. You just don't. You got to enjoy some biology. I mean, but even me as a chemist, I enjoyed biology. I mean, biology is nothing more than living chemistry, if you want to think of it that way, okay? And so, but she wanted to understand things a little more at the molecular level than at the systems level that you probably learn in biology, okay? What else did you learn about her? How many people here are thinking about the med track? Okay. So why should you have paid attention to what Madison had to say?
Well, she talked about the MCAT in the video.
She did talk about the MCAT.
She also talked about volunteer work, research
Yep.
opportunities that she did.
Yep, so not only was she a double major, she did a lot of other things too, didn't she? Can you highlight any of those things?
She went to Boston to study celiac disease at Harvard Med.
Yep. She was in Boston for, I think it was a summer. Went there and did some research. Certainly something a little different for her resume, right? What else? So for those of you who are thinking about medical school, how many of you are currently doing volunteer? Don't raise your hand, you don't have to. But I mean, think about, are you already getting involved in those volunteer things that you've got to be doing? Are you thinking about spending a summer somewhere else to make your resume stand out? You're going to have to write a personal statement for medical school, and it can't be a vanilla flavored personal statement. They read 100 of those at a sitting. You want yours to be something that stands out. There are more people who are perfectly qualified to be physicians than there are slots in medical school. There are people who would be excellent doctors but can't get into medical school. So if all you're focusing on is your grades and that kind of thing and your MCAT score, they've got plenty of people to fill their slots. They got more than enough people with good grades and a good MCAT score to fill medical school. So what you need is something that's going to separate you from those other individuals. And even then it's difficult. One of the things that I don't think Madison talked about is she applied all over the United States and really only got 2 interviews. Double major, 2 difficult majors. Music is not an easy major. Even if you know how to play your instrument well, it's a killer major. You're in practice all the time. I mean, it's amazing that she did it.
Especially at this school, because we're rated #1 in the nation, I think.
We're very high up. I don't know if we're #1, but we're certainly one of the best music schools in the country. Yes, but I don't know if our exact rank. But the hours and commitment just to being a music major is huge. Then she added biochem on top of it, which required her to do research, right? And she was thinking about med school and all the other things that she had to do. So her resume was filled with all this great stuff, and she still got maybe she got 3 interviews out of all the places she applied to. Why is that? Again, more qualified applicants than there are slots. And most state schools have a mandate that they take mostly in-state students. So if you're from Mississippi and you want to go to UAB, you're not an Alabama resident. That's already a strike against you, right? Not to say you can't get in, it's just much harder to get in if you're not a resident. So that's something to keep in mind, okay? But fantastic student, fantastic work ethic, got into medical school. She's now on the, she didn't talk about this here, she's now on the MD PhD track at UMMC. So she's doing research. Does anybody know what an MD PhD, what that means?
It's about an 8-year track, and you spend about the first 3 years doing med school and another 3 doing like grad school work, and you're getting credit for both at the same time, and you can do research in a specific focused field. Like I know UMMC has like biochem, neuroscience, biomed, stuff like that.
Mm-hmm. Yeah. What are the advantages of being a doctor? MD, PhD is doctor, right? So
You can do like more research, but also still be involved with your patients at the same time.
yeah, so if you're interested in not only being a physician, but being somebody that helps develop the medical field, this is something you might want to think about, is being an MD, PhD. What are some of the other advantages of being an MD, PhD? They usually pay for your medical school, okay? So medical school is not cheap, even at UMMC. It's expensive. But if you're on the MD, PhD track, you usually get a fellowship that covers your tuition, and you usually get paid. You get a little bit of money, okay? You don't make a ton of money, but that's more than most medical students get, right? But you are going to be, it's going to be high pressure. You're going to spend part of your time doing research. You're going to spend part of your time doing the med school track. There's some things that overlap. But at the end, you'll have the ability to not only be a practicing physician, but also be a medical researcher. And so that was her goal all along. I can't remember if in the video she talked about it. And so for her to actually get into the MD, PhD piece there was a happy day for her, I know for a fact. So I will show some more videos of things from previous students along the way. Some of them going to medical school, some of them went straight into industry. So you can kind of get an idea of how our students do. All right, so today I'm going to talk to you a little bit about what I do in my research, just to kind of give you an idea. Let me see. We'll just go with that presentation. And I'm not going to go through all the slides. This is a presentation I gave to some big shots several years ago. And so I'll talk a little bit about some of what we do. But I want to start off by just saying that in my lab, we do collaborate with people across the country and across the globe. So on the left here is the seal for the University of Greifswald in Germany. Greifswald is in the old eastern part of Germany where the Soviet Union occupied for many years. But of course now it's one unified Germany. You all probably don't know when it was split personally. I remember that when I was a kid. And so that's always kind of fun. We did actually get to travel to Germany and see what they do. We also collaborate with companies. Enzymicals is a company that actually is based in Greifswald. It was formed by our collaborator there, and they make enzymes that do interesting chemistry. And so in my research world, we use a little bit of biotechnology and a lot of organic chemistry to do new things. That's what we do. And we're interested in this concept called chirality. Okay, chirality is Greek, or chira, as they call it in Greek, and it means handedness. What is special about our hands?
They're mirror images of each other.
They are mirror images of one another, but they're not the same, are they? Everything has a mirror image. Your pencil has a mirror image, but it is perfectly superimposable on itself. Your hands are not. Why is that important? Why does that matter?
Difference, mirror images,
Okay.
Bless you.
Yeah, there are different properties to some level, right? I can put my right hand in a right-handed glove, but I can't put it in a left-handed glove, right? But I can put my socks on either foot. So what does that tell me? It tells me that socks aren't chiral. Gloves are chiral, okay? And so right hand, left hand. So we're always interested in how we can make molecules that have this one-handedness, either the left-handed version or the right-handed version, okay? And there are some examples from history that I think you should know about. Thalidomide is one example. Thalidomide was actually given to pregnant women many, many years ago to help stop morning sickness, to help stop the nausea, right? It's one of the bad things about pregnancy is nausea, okay? It's something that scientists and physicians thought, well, we can come up with something. And in fact, they did. And it was this thing called thalidomide, okay? And if you look at those molecules, you'll just have to trust me on this right now, but you'll learn this in organic chemistry. These are mirror images of one another that are not superimposed. One is the left hand, one is the right hand, okay? And it turns out that the left-handed molecule treats nausea. But it turns out that the right-handed molecule is a teratogen. Anybody know what that means? Not cancer necessarily, but it goes in and it alters DNA. Okay, and so unborn fetuses were born with terrible birth defects. It caused terrible birth defects. And so giving one version of this might be beneficial, right? But giving both versions of this turns out to be a problem. And it turns out that they were giving what was called a racemic mixture, meaning equal amounts of both hands, okay? And there's other biological things that go into that we won't get into. But anyway, this is why it matters, right? It probably matters more for you after you leave class. You leave class, you got a headache, you might want to go and take an Aleve. Why might you want to take a Aleve? What does it do? Reduces fever, reduces inflammation, reduces headaches, right? All right. It turns out that Aleve also has this handedness. You want this one. This one is the one that relieves your headache. You do not want this one. It is a potent liver toxin. It will kill your liver. What's bad about killing our liver? We've only got one. We don't have a backup liver, right? So that becomes a problem, right? So when you go and you buy Aleve, it has to be 100% this hand. Can't have any of that one in there, it becomes toxic. So what are you depending on? You're depending on the people who make it that know how to make one hand.
Is that what we use for rat poison?
Huh?
Is that what we use for rat poison?
Nope. No. The liver toxin one?
Yeah.
No. Rat poison is something different. You could probably kill rats with it, but no. So you got to have chemists that know how to make that hand and only that hand, right? Because you don't want any of the other hand in there for that to be. And it turns out that this isn't easy to do. In fact, when you look at the previous Nobel Prizes for chemistry, most of them go to how do you make one hand of a molecule. That's where most of our Nobel Prizes in chemistry, at least in the modern times, have come from, okay? Because it's important, it matters, okay? And so in our lab, what we do is we actually use enzymes to help us give us the handedness that we want. Because it's difficult for a chemist to go in and do it, but nature has figured out a way to do this, okay? And so we take molecules that look like this, don't worry too much about what they are. We use an enzyme which actually makes a chiral molecule. It only makes one hand of that molecule. And then we can take that molecule and we can make other things with it. In a nutshell, that's what I do in my lab, okay? And so it turns out for us We get some of those enzymes from Enzymical and pigs. Did you say that was cute? You like pigs? No, but that's cute. It turns out that pig livers have this enzyme called pig liver esterase, surprise, surprise the name, that actually do this chemistry and can give me one hand of my molecule, okay? When I first got started in this, we literally took one time a pig liver, put it in a blender, blended it up, and were able to get the enzyme that we wanted out to do this, okay?
The cuteness is gone.
Huh?
The cuteness is gone.
So, what's the problem with that though?
You gotta kill
More
more
bacon.
pigs.
Yeah, people are killing pigs all the time. I don't have to actually go kill a pig, right?
It's a one-time thing.
It is a one-time thing.
Being able to produce enough of like, I guess predicting that mechanism and then being able to produce enough of it each time.
Okay? I'll buy that. What else? Can all people in the world use something if a pig's touched it?
No.
No. No, there are religious considerations, right? So if I use a pig liver to do something, anywhere along the way, there's a certain portion of the population that won't be able to, for religious reasons, be able to use the products we make.
There's also people like with Lyme disease, things like that, when you can't, like AGS, the Alpert-Yau syndrome.
Mm-hmm. Okay. So how am I gonna fix that problem? Well, it turns out Enzymicals comes to the rescue. Enzymicals took the pig enzyme and then using biotechnology, allow that enzyme to be manufactured, so to speak, in E. coli. So E. coli make the enzyme that we use now, not the pig. So interestingly enough, it goes from religious concerns to no religious concerns in that regard, okay? And so, but they can also engineer and improve upon the enzyme from the pig. And so we get a lot of that kind of stuff from them and study the various pieces of it. So it's kind of cool. It turns out that this enzyme from the pig is what we call a promiscuous enzyme. It will work on a lot of substrates. One of the things you will learn in biology and biochemistry is that enzymes typically only work on their natural substrate. That is not true. Okay, that is one of the things that chemists have shown to be false. It just so happens that when we're studying it in nature, that's the only thing it works on, right? But the pig liver, given the fact that the pig has this terrible diet, or nasty diet, I like to think, it had to have enzymes that could digest a variety of different things, right? That's what the hypothesis is. And so we believe that that's why the enzyme will work on a lot of stuff. And so it works on these things that don't exist. I mean, none of that stuff that we're working with exists in the pig diet. But the pig liver will work on it and make that chiral molecule as one hand, which is kind of nice. And so then we could take it and make these amino acids, okay? And we make what are called unnatural amino acids that are useful for a variety of purposes, okay? And here's one of those purposes. So this is a molecule called somatostatin. This is one of the first things that we studied when I got here 20 years ago. So again, I'm an organic chemist, but here's some biochemistry, right? It turns out that somatostatin, it's a small protein or peptide. All of these little circles represent an amino acid. Okay, they're connected together and make this loop through this so-called disulfide bond between these two cysteine residues. Okay? This is the part in red that the protein, or that this uses to bind the cells. So cells have what are called somatostatin receptors, and the somatostatin will bind to the cell, and then that triggers a response. Okay? But interestingly enough, cancer cells quite frequently overexpress somatostatin receptors. In other words, if you look at a cancer cell, there's more receptors on the cancer cell than there is on a normal cell for somatostatin. Why might that be important from a medical point of view? Pardon?
If you can detect that, you have an indicator for cancer.
Okay, that's true. We could look at that and use that as an indicator for cancer. What else could I do?
Target them.
What did you say?
Target them.
I can target them. Why is that important? And maybe that's what you were talking about. Why is it important to be able to target a cancer cell? Is chemotherapy healthy for you or harmful? Yeah, we're giving you poison. We're slowly killing it. And we're hoping that it kills the cancer faster than it kills you, right? That's exactly what we're doing. So, but if I could target it to only the cancer cell, that would be the holy grail, right? If I could deliver this toxic substance only to the cancer cells, that would be kind of cool, right? And we can do that to some extent by using this overexpression of the somatostatin receptor. So you can imagine taking somatostatin and attaching the drug to it, and then that getting delivered mostly to the cancerous cell. So what's the problem with using somatostatin for that then? I've drawn some arrows up there. What do you think those arrows are for? Pardon? I could use those as points of attachment, but the point of attachment would probably be at the end. These are points of concern. Why would I be concerned here, maybe? How long do you think a small protein like this lasts in your body? Do you think it's real stable and lasts for a long period of time, or do you think it degrades pretty quickly? It does degrade very quickly, kind of like that first paper we were talking about, right? How to degrade things. Your body will take this and in a couple of minutes destroy half of it. So if I'm giving you a shot of this with a drug on it, in a minute or two, half of it's gone. Your body's processed half of it, which means you've only got half left. And then another couple minutes, half of that's gone. So how much time does it really have to get into your circulatory system and get to where it needs to be? Essentially zero, right? So what do I need to do? I need to make this more robust. And those points of concern are where your body has enzymes that cut this up, right? And so what we were trying to do was find unnatural versions of amino acids that we could put in there that would allow this to bind to the receptor, but it wouldn't degrade as fast. We were trying to figure that out, okay? And if we could figure that out, maybe we could address some of this stuff with pancreatic tumors, acromegaly, cervical cancers, and endometrial cancers. All of those cancers are known to overproduce somatostatin receptors. So it turns out we did a collaboration with some people at LSU Health Science Center. We built these things, we looked at them. Turns out none of our stuff worked. That's science sometimes. But that's the idea, right, was to take some of these unnatural amino acids and do this kind of work, okay?
So did the research die out?
No, we're just doing other things with it now. So no, it I'll skip through all that. The other thing that we've gotten into is potential antimalarial. So here's an example of where it does work. I'll show you an example of where things do work. So we made this molecule. Okay, your body has a lot of what's called glutathione in it. You'll learn about this in biochemistry, so don't worry too much about it right now. But glutathione looks like this, except where you see those little dashed lines, there's a hydrogen, and what we've put there is a carbon. So we've made it unnatural. Okay? And it turns out that there's the normal glutathione, and what happens is glutathione gets reduced to what we call GSH. Okay? And you have to have a healthy balance of GSH to glutathione in your body under normal, healthy conditions. Okay? And it turns out that this little parasite that causes malaria is very sensitive to those changes. So if we can actually inhibit the glutathione reductase and mess up this ratio, it might serve as a potent antimalarial, okay? Or a potential antimalarial. And in fact, don't worry about these graphs too much, but it turns out that our version of glutathione, our unnatural version, inhibits glutathione reductase from doing its job. okay? And so you might imagine being able to give this to somebody to help treat malaria, okay? And so we studied that for a while, and it works. It could be an anti-malarial kind of compound. So again, biologically relevant kind of questions. I'll skip over that real quick, and we'll stop there. So we've got a lot of things that we do with this type of work. Does anybody have any questions about that? So I don't work with too many undergraduates anymore, given my role as an administrator, but I still do take 1 or 2 undergraduate students every year. And I used to work with maybe 8 or so undergraduates at a time. Now I just 1 or 2 at a time. And so if you're interested in any of this type of work, I'd be happy to talk with you as you get a little further along. I would prefer that people, if they want to work in my lab, have at least been through organic chemistry, because we do a lot of organic, but yeah.
When you're making like chiral molecules, how do you just make it into separate racemic mixture, or are you making one hand at a time?
Yeah, so we can do both. We can make it to where it's just a racemic mixture and then separate it. But I'm making something that I'm not going to use, and I have to throw that away, right? But that's the beauty of the pig liver esterase. It takes my molecule, which isn't chiral, and it predominantly only makes one hand of the molecule. So pig liver esterase can get pretty close to 100%, depending on the substrate. You get pretty close to 100% of the hand that we want. And so once we have that, then we can do all the other chemistry we need to do to make whatever it is that we're interested in. So that's what the enzyme does for us. So the enzyme, you can think of it as the glove, right? And the substrate then comes out as the correct hand. So that's the way that we kind of think about that.
I guess you don't always, like, the different reactions don't require enzymes sometimes, like.
No, we use the enzyme to give us the handedness, and then we do regular organic reactions for the rest of it. So to convert that molecule into whatever amino acid we're interested in, we just use standard chemistry at that point, which we didn't talk about. But it's an area that I still find fascinating, being able to make one hand of a molecule. That's kind of been my drive. Ever since I was in graduate school, we've always worked with handedness, and it's something that I'm always excited to see the Nobel Prizes win. This year, the Nobel Prize had nothing to do with handedness. It's all those quantum dots, remember? Last year was the year before last was, so 2 years ago, was handedness. That was Dr. McMillan at Princeton, who was making these organocatalysts. And we found ways to make things similar to what he was doing through our methodology. So there are a lot of Nobel Prizes out there on this type of work. I will never get one, and that's okay. But
You never know.
no, I do know. I will never have a Nobel Prize. I sleep too much, and that's okay. Don't have to have a Nobel Prize to do good work, right? So, but our work is cited by people. Our work has been cited by people who have won Nobel Prizes. So, that's always refreshing to know that people value what you do. The cool thing about if you want to be an undergraduate and work in my lab is that most of my undergraduates, at some point after they leave, will end up as a co-author on a paper. That's true for most of our undergraduates that do research in our research labs here at USM. And I think that is something that sets us apart from other institutions. So not everybody gets a paper, but usually when you go into a research lab here in the chemistry program, at some point after you graduate, you'll get a phone call or an email from your professor, and they'll say, what's your new email address? I need to send you a copy of the paper that you're an author on. Because we do have you working on the stuff that we're trying to get published. And usually, if you're doing a semester's worth of research, you won't see that completely to finish, but you'll have contributed in a way that can get you that paper. And so people have used that in the past to, get into medical school, get into the graduate school that they wanted. Being able to do the research is very, very important in that regard. All right, just to remind everybody, we've got, I believe this Friday is the day that you have to turn in your redo for your semester guide. Just remember that you can get up all of your missed points back if you address everything. So don't miss out on that. That's an opportunity to get all your missed points back. So spend that. Also, you can go ahead and start. Some of you have already started emailing me about setting up times for the bonus. So you don't have to do it. It's up to you. But if you want some bonus points, which will make up basically a missed absence. So I think I've set it at 20 points. So if you're thinking, well, I've missed 2 classes and this is an opportunity to make up for that missed class, to schedule a time to come by and talk with me for about 15 minutes. So go ahead. When you do that, please send me an email and let me know 3 or 4 times that would work for you, okay? And then I will pick one that fits my schedule. Don't just ask, what times do you have? My times can be, my time is like gas. It fills the container. So I need to know what works for you. Huh? And it leaves. Yeah, it goes really quick. So just let me know a few days and times that would work for you, and I'll pick one that fits my schedule. That's the easiest way for me to do it because I don't use the fancy scheduling feature in Outlook. I probably should, but I don't. On your card, print your name, your ID number, turn those in on your way back or on your way out, and I will see you all next week.